Hey guys, I'm an astrophysics major, and today I'll be explaining general relativity in the easiest, most intuitive way I possibly can, as if I was explaining it to my high school self. This is the second video of a two-part series on Einstein's relativity, where my previous video was on special relativity, so I really suggest you watch that first. Let's get into it. Picture this. You're standing on Earth, and somehow the sun, which is 93 million miles away, is pulling on you. But how? There's nothing connecting you to the sun. There's no rope or chain. This bothered physicists for centuries. In 1687, Newton told us that the force of gravity reaches across vast distances to hold the entire solar system together. His math worked incredibly well for most situations, but even he admitted that he has no idea what this force actually was or how it even worked. So something was missing from the picture. In 1915, which is 10 years after Einstein proposed special relativity, he proposed general relativity. In general relativity, he asked, what if gravity isn't really a force at all? Instead, he said massive objects like the sun actually bend the fabric of space-time itself. So you can think of space-time as a stretchy trampoline or sheet, and when you place a bowling ball to represent the sun, in the center, it creates a dip in that trampoline or that sheet. Now, if you roll a marble to be the Earth nearby, it doesn't roll in a straight line anymore. It curves around that dip. That's basically what's happening in our solar system. The sun isn't pulling Earth, but instead, the sun curves the fabric of space-time, and Earth just follows that curved path. Okay, so how do you test such a crazy idea? So, in 1919, astronomer Arthur Eddington had a brilliant plan. During a solar eclipse, he photographed stars that appeared near the sun in the sky. But why during an eclipse? Because normally the sun's bright light makes it impossible to see nearby stars. But when the moon blocks the sun's light, those stars become visible. So, here's what Eddington discovered. The stars near the sun appeared slightly shifted from where they should be. It was as if the sun had bent the light from those distant stars. This was clear evidence that the sun really does curve space-time. Okay, that's confusing. Let's backtrack a little bit. So how did Einstein even come to this crazy idea that space-time was bending? It all started with something he called his happiest thought. Einstein was watching a worker on a building, and then he imagined what it would be like for this worker to fall. I know, what the heck. While he was imagining this, he realized something extremely profound. If you're in free fall, ignoring air resistance, you feel completely weightless. You'd float around just like an astronaut in space. But here's where it gets interesting. Einstein asked, what's the opposite of free fall? It's standing on the ground where you feel your weight, right? So now imagine you're on a windowless elevator in space, and if that elevator is accelerating upwards at 9.8 meters per second squared, you'd be pressed against the floor with the same force that you feel standing on Earth, right? You literally cannot tell the difference between standing on Earth with gravity pulling you down versus being in a rocket or elevator accelerating upwards in space at 9.8 meters per second squared. So this comparison led Einstein to an extremely startling conclusion that maybe there's no difference. Maybe what we call gravity is actually just the experience of being accelerated and not a force pulling us down per se. Einstein called this the equivalence principle. It basically says that the effects of gravity are completely indistinguishable from the effects of acceleration. This is similar to what we learned about special relativity. You can't tell if you're moving at a constant speed versus if you're standing still without looking outside, right? Now, Einstein was basically saying that similarly, you can't tell if you're experiencing gravity or acceleration without looking outside. When you're standing on Earth, you think gravity is pulling you down. You think in classic Newtonian physics, there's some sort of invisible chain pulling you down towards Earth. But Einstein says, no, it's actually flipped. When you're in free fall, you're actually following the most natural path through space-time. You're not being acted upon by any sort of forces at all. Think of it like you're rolling down a hill, you're just following the natural slope. Because remember, Earth's mass has created a dip in space-time, right? Some sort of steepness. So now you falling down is basically you just following the most natural path along the curvature of space-time. Only when the ground interrupts your natural motion once you hit it is when you feel the weight. The ground is literally accelerating up onto you, preventing you from following your natural path through curved space-time. You're probably thinking, okay, hold on. If the ground is accelerating upward, wouldn't Earth be expanding in all directions, right? Why aren't we flying away from each other? So this is where Einstein's insight gets really subtle. This ground's acceleration isn't making Earth bigger because it's keeping Earth from collapsing under its own space-time curvature. Okay, think of it this way. If you were to turn off all of the upward acceleration in all directions of Earth, the entire planet would collapse inward and everyone and everything would be falling towards their natural path. So it's because of that upward acceleration in every direction of Earth's surface that Earth isn't collapsing within itself from its own curvature that it's causing. So I keep talking about the most natural path through space-time, but let's talk about what they really are. These paths are called geodesics. Imagine you want to walk from the south to the North Pole in a straight line. From your perspective on Earth's surface, you're walking straight, you're taking it step by step by step. But from someone watching you from space, they would see you following a curved path around the globe. That's because you're walking along the geodesic, the straightest possible path on Earth's curved surface. The same thing happens in space-time. Earth appears to orbit the sun in a circle, but what's actually happening is that it's traveling in a straight line, but because it's on the sun's curved space-time, the straight line appears as a circle. So you're probably asking, okay, if Earth is constantly falling towards the sun, why doesn't it eventually fall into it? And the answer is orbital velocity. So Earth is indeed falling towards the sun, but it's also moving sideways so fast that it doesn't fall in. It's like throwing a ball so hard that it goes around the entire Earth and comes right back to you. This is exactly how the International Space Station orbits Earth. Technically, the ISS is constantly falling towards Earth, but it's moving sideways fast enough to where it's not going to fall into Earth. So I know I showed you an example of a bowl and then a marble going around that bowl. But imagine in the frictionless environment of space, this can continue going on indefinitely. It's not that gravity is holding it together, but more so that the planets are following their geodesics, their straight lines, and their surface happens to be curved. So that's how planets are able to orbit around the sun. Now here's where it gets even stranger. Einstein realized that if massive objects curve space, they must also curve time. And this is because space and time aren't separate things, they're woven together into a single thing called space-time. So this means that time actually runs slower along stronger gravitational fields. So someone near a very massive object experiences time more slowly than someone far away. This is called time dilation. Imagine if you're putting a bowling ball on a stretchy rubber sheet, you can see that where the bowling ball is where the sheet is most stretched out. Now, if you imagine that sheet to be space-time, you can understand that someone near a massive object experiences time more slowly because it's stretched, as compared to someone who's farther away from that massive object and farther away from the influence of that curvature of space-time. This is why GPS satellites have to account for the fact that time actually runs slightly faster in their orbit than it does on Earth's surface. Without these corrections, the GPS would be off by miles. So now let's talk about an extreme case in general relativity. Remember how I said that if Earth wasn't accelerating upwards in all directions, it would collapse inward due to its own space-time curvature? Well, there is a body out there that is so incredibly dense that it bends space-time curvature enough that it does collapse within itself. And I'm sure you've already guessed that these are black holes. With the help of mathematician Karl Schwarzschild, general relativity predicted black holes before we even ever found one. A black hole has way over 1 million times the mass of the sun, but it also has virtually zero volume. So you can imagine that this is extremely dense, infinitely dense. Thus, it curves spacetime to an extreme degree. The curvature of spacetime from a black hole becomes so steep that once you cross a certain boundary, which is called the event horizon, even light can't escape. At the center of a black hole, math predicts something called a singularity. This is the densest part of a black hole, it's infinitely dense, and this is the point where our entire understanding of physics completely breaks down. Now, we don't know if singularities actually exist or if they're just a sign that we need better theories, but what we do know is that near a black hole, the curvature of spacetime has dramatic effects. Time dilation becomes extreme, as shown in the movie Interstellar, where 1 hour on a planet near a black hole equals 7 years on Earth. So, Einstein's general relativity completely revolutionized our own understanding of reality. It showed us that gravity isn't a force per se, it's the geometry of spacetime. It's the effect we feel when something like the ground resists our natural motion along this curved spacetime. So, as John Wheeler said, matter tells spacetime how to curve, and spacetime tells matter how to move. General theory of relativity has been confirmed countless times and has had practical applications on the global positioning system, astronomy, and our general understanding of the universe itself. Most remarkably, this all started with Einstein imagining how it would feel to fall off a building. So remember, the next time you're experiencing your weight, which is right now, I would hope, remember you're not being pulled down, you're being prevented from following your natural straight path or your geodesic through curved space time around you. Hope that helps, and thank you.